This week, the autopsy of a major city, its subterranean bowels, congested arteries, and threatened flora. A city is an ecosystem, that is, a community of living things together with their environment. A city has a fauna and a flora. It consumes energy and produces waste. A real living, breathing organism. However, what we see at its surface is only the tip of the iceberg. Its vital organs are hidden underground. On the surface, a major city is millions of human beings moving about, nourishing themselves and consuming energy to live. Under the ground, however, it is an endless network of galleries dug at different depths. Well-defined infrastructures are found at every level. In the first 5 meters, the quality of the soil is often poor. It may be backfill, residues from construction work, for example. As a rule, it is in this upper layer that the conduits for electricity, gas, compressed air, or drinking water are laid. A little farther down, the subsoil is generally firmer. It may be composed of sand, gravel, or clay. It is at this level that the sewer pipes and subway tunnels run. As subway networks are extended, they move down into a third, harder level of soil which does not sink. This is the parent rock on which the city is erected. It is often limestone, a rock that is easy to dig. A subway will sometimes go down 30 or even 100 feet deep. The city's drinking water from nearby springs or rivers is also stored at this level. Aqueducts channel the water into the urban area. The water flows through these massive concrete pipes by simple force of gravity, since the source is generally located above city level. The water is captured and stored in huge concrete reservoirs, tiered at various levels. The water is pumped up from one reservoir to the next. Each reservoir serves, again by gravity, a given district in the city. For instance, the upper reservoir, which may be located in a hill, will serve the highest part of the city. The water is distributed by a network of metal pipes that run under all the streets in the city. A system of gates controls the distribution to consumers according to demand. The water mains are located in the same superficial layer as the sewer pipes. It is through the sewers that a city is able to discharge its vast amounts of solid and liquid waste to the drains. Every building, every street is connected to the sewer system by pipes which drain the liquid waste. The wastewater is first collected in small drains called lateral sewers, then in larger secondary drains. Finally, main sewers discharge the liquid wastes to the purification plant. Rainwater follows the same course, but exceptionally, when there are major storms, the excess water is automatically pumped into the city's main water course. The liquid wastes flow into the drains by gravity. However, regular maintenance is required, since the sand and gravel the water drags with it can build up and obstruct the pipes. The first step in sewer maintenance consists of wash boring. Any inert matter goes into a detention tank or a sand catcher. The sewermen extract it by machine and send it to landfills. The working conditions of sewermen are particularly harsh. When the water stagnates, for example, the matter ferments on contact with the air and releases such toxic gases as hydrogen sulfide or methane. Fortunately, the manual systems will soon be replaced by automated ones. The subway tunnels are laid just below the sewers. Here, the job no longer simply consists of channeling massive amounts of wastewaters, but ensuring the transportation of millions of travelers. This requires rigorous organization. At the same time, every day, the power is turned on in the station. The first conductors enter the station. As the city awakens, new trains are put into service. They are closely monitored by teams in control booths. A display panel keeps track of the position of the trains and signals at all times. The nature of the soil greatly influences the development of a city's underground infrastructure. The equipment used in the old days was not good enough to dig down very deep. That's why in the first 10 meters of urban subsoil, there is seldom any room left to build tunnels. Today, however, we can dig deeper, at least in hard rock such as limestone. Rock that tends to cave in hinders the development of underground infrastructures because it becomes very expensive to tunnel it. This type of soil also puts limits on a city's capacity to build up, as it were, because it will not withstand the weight of skyscrapers. Cities such as these, less favored by nature, have no alternative but to grow horizontally by spreading out, often at the expense of green spaces or farmland. When he launched 1,000 cars in the streets of the cities, Henry Ford thought he had found a democratic solution to the problem of urban transportation. Today, it's a nightmare. Some feel that cars should not be allowed in cities' downtown areas. Meanwhile, engineers are busy trying to unblock the city's arteries. Without efficient transportation systems, a city would never be able to function. Modern communication tools, such as the radio telephone and the fax, will never completely replace direct contact. Direct contact means a lot of getting around in a city, which in turn means the proverbial traffic jam. Traffic jams occur when too many vehicles get onto the same road. Any obstruction in the flow of traffic will create a traffic jam. For example, an intersection that suddenly becomes congested at rush hour will cause a holdup whose effects quickly ripple down to every street in the vicinity. Similarly, a red light or a blocked street will break the flow of traffic and cause motorists to lose a considerable amount of time. On freeways, a traffic jam often causes disruptions that propagate by regular stages, forming bumper-to-bumper areas. This is the slack action motorists know only too well. Fortunately, increasingly sophisticated methods of control are being introduced to improve the flow of urban traffic. One such system has to do with traffic lights. In conventional systems, traffic lights are regulated in a predetermined fashion, programmed at regular intervals. For example, the light switches to green every 20 seconds. Today, a number of cities are replacing this old system by a more flexible one. With the new system, the light's duration can be made to vary according to the number of vehicles driving through each intersection. They will also adjust to changes in traffic flow during the course of a day. This is done by permanent surveillance systems that collect data on road network flow. That is the number of vehicles passing on a road per unit of time. This data is usually provided by magnetic loops installed under the pavement. Such traffic detectors relay the data to computer cabinets set up along the roadside. It's these crossroads controllers that will switch virtually instantly the traffic lights at an intersection. The data can also be relayed by cable to a master controller. The master controller is equipped with a powerful computer capable of managing the traffic lights of several hundred intersections at a time. This makes it possible to control traffic flow at certain intersections to prevent congestion at other intersections. A system like this can reduce city driving time by about 20%. The same principle will control electronic display panels. Linked to a master controller, these variable message panels notify motorists of a traffic jam several kilometers away and indicate the direction they should take to avoid it. The message changes according to traffic conditions. However, the system has a drawback. It gives all motorists the same message. As a result, hundreds of drivers head towards the same detour, where they may end up creating another holdup. More advanced systems are currently being developed to improve traffic flow. They consist of information techniques designed for individual users. For a number of years now, many motorists have been using radio guidance. Thanks to radio stations that provide ongoing traffic reports, drivers are able to change course according to traffic conditions. Other, even more advanced techniques, such as interactive guidance, are currently under study. Interactive guidance allows the driver to select the best route by consulting a specialized center with a microcomputer in his vehicle. Signs along the roadway provide information on traffic conditions. These data are radioed to the vehicle's microcomputer, which processes the data and proposes to the driver by way of graphic display the best route to his destination. A short written text or a synthesized voice message will also give him additional information. All these new systems are designed to provide individual drivers with information that concerns their particular itinerary only, as well as general information on traffic conditions. But the technology raises the touchy problem of the confidentiality of information. In order to direct a motorist, the guidance center needs to know his point of departure and final destination. The sensitive issue here is to prevent information on the comings and goings of motorists from being intercepted and used to other ends, by the police, for instance. Solutions to such problems will have to be found before motorists will be willing to accept systems such as these. A great deal of effort goes into improving the quality of life in cities. Creating green spaces, for example. A city may not be the best place to plant trees, but the scientists are doing their utmost to make it possible. Trees are living things which, like us, have to adapt to the difficult conditions of city life. Continually subjected to polluting gases, winter snow removal salt, or injuries inflicted by car bumpers, the urban tree presents pathological signs quite unlike those of forest-grown trees. This is of some concern to researchers who are unsure of how to treat these particular diseases. Dust is one of the main causes of the degeneration of city trees. Normally, plants carry out all their vital functions through minuscule pores located under their leaves. It is through these pores, also called stomata, that the plant receives the carbon dioxide crucial for photosynthesis. That biochemical reaction ensures the production of the substances a tree needs to grow. The oxygen that results from photosynthesis is also released through the stomata. The same goes for part of the water the tree has absorbed. However, when dust or soot blocks the stomata, these exchanges cease to take place. The particles of dust may also obstruct light, essential for photosynthesis. Trees thus affected will ultimately die. One of the solutions to the problem of tree degeneration is to use hardier species. Oaks, plane trees, elms are a few examples of trees that adapt well to city living. The ginkgo withstands pollution particularly well. Up until now, the ginkgo, which has been in existence for millions of years, suffers from no known diseases. In addition, the ginkgo grows fast and straight, which makes it all the more attractive to urban planners. Still, it is not enough to diversify the species. The researchers must, above all, understand why and how urban trees become sick. In their natural habitat, every species tends to develop a characteristic disease. In a city, the problem is far more complex. Trees often become sick following a trauma of some sort, such as an injury. Traumas foster the proliferation of pathogenic microorganisms that will gradually cause the tree to die. In the last few years, researchers have used artificial intelligence to diagnose the diseases afflicting urban trees. They draw up a detailed inventory of the organisms which develop as a result of a given trauma, such as pruning. There are several ways to prune a tree, but they all entail injuries. Before the tree has time to heal, fungi and bacteria can get into its vessels and weaken it. Once the researchers have identified the types of microorganisms characteristic to each species, they will be able to develop diagnostic software. Such computer programs will help save thousands of trees. The nature of the soil can also be a stress factor for city trees. Urban soil is often of very poor quality. For every planting, each tree must be provided new soil, whose quality is laboratory tested. But none of these measures protect the tree from the dangers of soil compaction. Whenever a car parks too close to a tree, for example, its weight packs down the earth, preventing water and nutritive elements from reaching the tree's roots. If this occurs on a regular basis, the tree will quickly degenerate. The problem can, however, be avoided by raising the curbs and installing protective grates that prevent cars from compacting the soil near the tree. Other studies should help to better integrate trees to city landscapes. They deal with the pattern of growth of various species of trees. Patiently, the researchers observe every one of a sprout's countless stages of development. Their observations are translated into numbers and processed by a computer program according to simple mathematical rules. This modeling phase enables them to simulate, in computer graphics, a tree's growth. All that's required is that the mathematical equations be put into images. Owing to this research, it is now possible to predict, for example, a tree's size at maturity, or select the best way to prune it. All these approaches are part of a recent trend to give plants primacy over concrete. The obstacles are many. There is a severe lack of space in major centers. Moreover, it is less expensive to maintain a concrete space than a green one. Nonetheless, progress is being made. Creating gardens on city flagstones is an example. It's an exciting idea, but it still poses numerous technical problems. Much research is being done in this area, for if we are to believe the experts, flagstone gardens may prove to be the answer to the problem of the lack of green spaces in cities. A city is, of course, concrete, high-rises, and traffic jams. But it's also the corner store, the tree in the schoolyard, and the two-steeple church.